Okay, so it's my pleasure to have Vishesh on our seminar. He's one of these great MIT graduate students that did lots of impressive work recently, and he's now in Stanford. And he will speak about one of the works on discrete random matrices. Thanks for giving the talk, Vishesh.
Thank you very much, Andre, for the invitation and the kind introduction. So today I'm going to talk about the singularity of discrete random matrices. I think it's a good thing to talk about in Russia. It has some history here, this problem. And this is joint work with Ashwin Sai and Mehtab Sahani, who are like amazing graduate students at MIT. Must have heard of them, and you should invite them to give a talk at some point in the seminar, right? Okay, so Andre told me that there are like some Moscow students here, so I tried making like some parts of it introductory and self-contained, and at least my hope is that at least 2/3 to 80% of the talk should be like quite accessible and self-contained. So please stop and ask me questions. We have a lot of time, and I don't have content for 90 minutes. And maybe the last 10 minutes will be a little bit fast, but that is just me hiding all of the hard details at the end, right? Okay. So let's start with the question. Okay. Yeah. So here's the basic problem. Okay. So let's say you have like an n by n random matrix. So this is the basic model. This is maybe the foundational problem of this field. So you have an n by n random matrix, and let's say each entry is an independent Bernoulli 1/2 random matrix, right? So I have n squared entries, each entry with probability 1/2 is 0, probability 1/2 is 1. And the question here is, what's the probability that this matrix is singular, right? Okay. So singular in the sense of linear algebra, it has like a non-zero null vector, right? Okay. Or the determinant is 0. Okay. So if you think about it for a moment, you will come up with a lower bound, and the lower bound will look something like this. What is this thing? So okay, if you compute the probability of 2 rows or 2 columns being the same, or a row or column being 0, then you'll come up with a number which looks like this. And this is clearly a lower bound on the singularity probability, right? And now you might ask, okay, is this the dominant mechanism, or is the singularity probability higher, or can I say something about it, right? Okay. So it turns out that, okay, even though there is this lower bound which is rather small, and it seems, if you think about it, it seems like, okay, this is some obvious reason for the matrix being singular. And then if you think a little bit about it, doesn't seem to be any other way for the matrix to be singular. Somehow proving any sort of upper bound on the singularity probability is not very easy, right? So there is this famous work of Combgeo from 1967, where he showed that the probability of a random Bernoulli matrix being singular goes to 0 as n goes to infinity, right? So Bernoulli matrices, random Bernoulli matrices are invertible asymptotically almost surely. I will actually show a self-contained proof of this thing later. So hold on for that. But now you might say, okay, the lower bound and the upper bound are kind of far away. So can we do better? So this actually took a while, and there was another famous result by Conglocious and Samiridi in the mid-90s, where they showed that, okay, we can't really do this good. We can't do this well. But they were able to show that the probability of singularity is exponentially small, right? So at least, okay, it's in the right ballpark now. And now the question is, can you do better on this constant, right? Okay, so this was again stuck for like 10 years. And there were a couple of works by Tao and Wu, and then another by Burgi and Wu and Wood. This used this so-called inverse Littlewood-Alpert theory. And these were able to give progressively better bounds on the base of the exponent here, right? So 0.75 and then 1/√2. And then again, the problem was stuck for a long time until 3 years ago, when it was resolved in some sense by Tikhomarov, right? So this is a spectacular breakthrough work. And in some sense, it resolves this problem. Okay. But now you might ask, okay, does it really resolve this problem? So what does Tikhomarov's proof show? It shows that the probability that a random Bernoulli matrix is singular is 1/2 plus little o(1) raised to the n, right? Little o n1 is some function which is going to 0 as n goes to infinity. So perhaps the way to interpret Tikhomarov's result is if you look at the log of the probability and divide it by n, it tells you that the limit of this thing is 1/2, right? Okay, so it's really a result about the log of the probability, or about the normalized log of the probability, and not so much the probability. And you might ask, okay, this motivating question which we had here, or this motivating lower bound which we had here, which gave not only a probability but somehow suggested a mechanism for singularity, right? So this lower bound is not just some arbitrary number; it has a meaning, which is that, well, up to leading order, or the dominant contribution to the probability of singularity is a row or column being 0, or 2 rows or 2 columns being the same. So it has some meaning, whereas a bound of this form doesn't really capture that meaning, right? So you might ask, okay, can I actually show not just the statement of this form about the log of the probability, but actually say something more concrete and precise, and say something about why the matrix is singular, right? Okay, so this is going to be the problem I'm going to talk about. So let's call this the strong invertibility of random matrices. And for motivation and also to discuss some previous results, let me focus on sparse Bernoulli matrices, right? So on the previous slide, I was talking about the case of Bernoulli 1/2. For the moment, let me switch to a slightly different distribution, which is Bernoulli P for P between 0 and 1/2. Okay, so why do I do this thing? So the reason for this is, well, when we think about Bernoulli 1/2, right, there are a bunch of things which somehow contribute equally, right? So the probability of a row or column being 0 is 1/2 to the n, but the probability of 2 rows or 2 columns being the same is also 1/2 to the n, right? So the singularity event is a little bit more complicated. So now you might say, okay, let me try to simplify this thing and see if I can actually prove a result of this form. So if you move to Bernoulli matrices for P, which is between 0 and 1/2, then the probability of having a 0 row or 0 column is exponentially more likely than having 2 equal rows. So then you might hope that, okay, in this case, things are a little bit more simple, and perhaps I can prove a sharp result here. Okay, so this is the strong invertibility of sparse Bernoulli matrices, which has been studied, I guess, in the past 5 years or so. And now if you think about the obvious analog of the singularity conjecture, it would be, well, the probability of singularity is the probability of having a 0 row or column plus some lower order terms. Okay, so this was the conjecture. And there was some works on this in the past 5 years or so. Okay, so let me sort of summarize this and say what is known here. Okay, so firstly, I said like P, which is between 0 and 1/2, and for when in this talk, P is going to be fixed, but people have studied this thing even when P decreases as a function of n, right? So there are works by Basak and Rudelson, then Litvak and Tikhomarov, and by Huang. And together, all of these works show that if P is at least log n over n, and at most some small constant, then this kind of result is actually true, right? Then the probability of singularity is the same as the probability of having a 0 row or column plus lower order terms. And below log n over n, you will have some isolated vertices, so you will be singular with high probability. Okay, so log n over n is the threshold. Okay.
Vishesh, sorry, just out of curiosity. So Huang, is this Hao Huang or
no?
A different one?
This is Han Huang, who is a Georgia.
Okay.
And Sasha Litvak and Konstantin Tikhomarov, you probably know, and this is Anirban Basak and Mark Rudelson. Yeah, absolutely. Thanks for the clarification. Yeah.
Okay, thanks.
Okay, so these results, put together, cover this regime from 1 over n log n all the way up to a small constant, let's say 1 over 100. So now you might ask, okay, what about P, which is between C and 1/2, right? And in this case, the techniques in these papers don't really seem to work, and somehow the best known result here is only about the log of the probability, and this is in the same paper by Tikhomarov, right? So it's the same kind of result here, where you can say something about the log of the probability, but not really something about the probability. But if P is smaller than, let's say, 1 over 1,000, then you do have all of these really nice results, which can give you this sharp answer. Okay. So now you might ask, okay, instead of like doing this distribution by distribution, can you say something in more generality? Okay. So here's like a general setup in which I want to work. So let's say I say that a random variable is discrete. Okay, if it's supported on finitely many values, right? So again, I'll only work with real valued random variables. People also consider complex valued random variables in some cases, but this leads to a bunch of other technicalities. So let me not go into that. So for us, a discrete random variable is going to be any random variable which is real valued and supported on finitely many points. And of course, I want it not to not be constant. Otherwise, this problem is not interesting, right? So something which is supported on 2 or more points, and these can be arbitrary real numbers. And now you can ask the same question, which is, okay, estimate the probability that the matrix is singular, right? Okay. So which matrix? Okay, so I have an n by n matrix. Each entry is an independent copy of C, which is this discrete random variable, which is fixed, and then n goes to infinity, right? So C is fixed, and then n goes to infinity. Okay. So in this case, the situation was actually not so great in the sense that even the log of the probability, right? So even results about the log of the probability were only known for some special choices. Firstly, there was this work of Tikhomarov that I mentioned for Bernoulli 1/2, but actually his paper deals with Bernoulli P for P between 0 and 1/2 fixed. And the second is this paper of Bourgain, Wu, and Wood. And they were able to handle like some sort of special choices of C, which come from Fourier analysis. So it basically are like things which work for the proof. And an example of something which works for the proof is if C is +1 or -1 with probability a quarter and 0 with probability a half. So it's like some lazy Rademacher, right? Then they can show a result of this form on the log of the probability. And then there are like some analogous kind of distributions that they can handle. But this was sort of like open broadly. And perhaps like the simplest case in some sense, which was open, was Bernoulli P for P bigger than a half, right? So now, so maybe like many people here do random graphs or something. And in these cases, you sort of get used to the fact that things are symmetric about a half in many cases. Here, this is very much not the case, right? Because when P is less than a half, then the dominant event is really a row or column being 0. But when P is bigger than a half, then the dominant event is 2 rows or 2 columns being the same, right? Because there is no possibility of a row or column. Well, there is a possibility of a row or column being 0, but this is like exponentially likely, right, compared to the other thing. So this is not a situation where P is symmetric about a half. And really, the mechanism of singularity is different, right? Because there it's really coming from a row or column being 0, and here this is something involving 2 rows or 2 columns. So this was actually not really under the, it couldn't really be handled by the techniques before, and this I think was like a good motivation for us to work on this thing. So can you say something about this thing, even like about the log of the probability for P between a half and 1 fixed? Okay. So now you might say, okay, let me be a little bit more ambitious and even like make some conjecture about the mechanism, right? So okay, it doesn't cost me anything, and it seems like it should be the same thing. So C is any, so okay, so again, what's happening? So C is a real valued random variable, non-constant, taking on finitely many values. I fix C once and for all, and then I take n to infinity. And I have this n by n matrix whose entries are populated with independent copies of C. And now you might say, well, okay, what should be the dominant contribution to singularity? Well, 0 row or column, 2 equal or opposite rows or columns, and then everything else seems like it should be lower order because it should involve 3 or more rows or columns, right? Okay. So or like maybe 2 rows being 0 or something, right? Okay. So this is a conjecture. I guess it appears in some form somewhere. And the result that we proved with Ashwin and Mehtab is, well, we proved like something stronger in some sense in terms of conclusion, with a caveat, which is that we cannot prove it for uniform distributions, right? So for any discrete random variable which is not uniform on its support, this conjecture is true. However, for the most basic case of Bernoulli 1/2, we don't really know how to prove this thing. So that's unsatisfying, but somehow it's true for like almost every random variable. Right? Okay. So I said this is like a little bit stronger than the conjecture, and the reason is just like the placement of these like 1 plus that low 1 terms. So it's some technicality, but let me just sort of say, for instance, what this means in the Bernoulli case. So for instance, if you look at like Bernoulli P, which is between 0 and 1/2, so I said, okay, for P which is between 0 and like 1/1000, this was known. But for P which is between 0 and 1/2, you actually even end up getting 2 terms of the expansion, right? So even the first term of the expansion was not known, but somehow because of this placement of the 1 plus that low 1, we actually end up getting two terms. And for instance, for Bernoulli P, which is between 1/2 and 1, we get the first term of the expansion. And for any random variable which is not uniform on its support, we will get at least one term of the expansion, and then sometimes we can get like two or possibly more, depending on what the random variable is, right? Okay, so this is sort of the first result. The second thing that you might say is, okay, what about uniform random variables, right? So what about random variables which are uniform on their support? Well, unfortunately, the only thing, the only thing that we can say here is we can get the correct value for the log of the probability, right? Like the normalized log of the probability. So okay, so this is sort of like one thing that we can do. We have like some other result as well, but that's a little bit technical to explain without context. So let me sort of not do that, but say that, okay, for uniform random variables, we get the log of the probability, and for non-uniform random variables, we get the probability, right? Okay, again, up to leading order terms everywhere. Okay, so these are sort of like the clean results, right? Now there is one other result I want to mention, which really just seems to come out of nowhere right now, and you might even question why I'm discussing this. But somehow it's going to be related to what's coming up, right? Okay. So now let's sort of move to a slightly different model of random matrices, right? So previously I had this thing where each entry was independent, and let's say it was like Bernoulli 1/2 or something, right? Now think about a situation where the entries are not independent, but let's say I'm sampling rows independently, and I'm sampling rows independently from the central slice of the Boolean cube, for instance, right? So I have like n entries, and it's a vector in 0, 1 to the n, and the sum is constrained to be n over 2. Okay. So now the rows are no longer independent, but you might say, okay, well, the probability of singularity is the probability that, let's say, two rows are the same. That's like about 1/2 to the n, or two columns being the same. That's like 1/2 to the n, right? Okay. So this was studied by Hoi Nguyen, or rather, like Hoi Nguyen was the first person to study it. And his motivation for this was really to sort of study models of random matrices in settings where the entries are not independent, right? So people like, I guess including us, have studied these questions about random graphs, random regular graphs, random regular directed graphs, and so on, and linear algebraic properties of these things. And these are cases where the entries of the matrix are not independent. So this guy was actually introduced as a toy model where at least the rows are independent, but the entries within the row are not independent. And he made this conjecture that, okay, the probability that I'm in the singular is 1/2 plus log 1 to the n. And of course, this seemed very hard at that time because people didn't even know how to prove this for the Bernoulli case, right? So anyway, High proved that the probability of singularity is polynomially small for like any polynomial. And then together with Asaf Ferber, Kyle Liu, and Wojtek Samotich, we proved some exponential type bound. And then Tuan Tran last year actually got an exponential bound. And one of the things we get in our paper is this resolution of the conjecture of pi. Okay, so that's one thing. But okay, the reason I mention it is not because to sort of highlight this result on its own, but somehow what happens so this model was really introduced to study dependent models like random graphs or dot graphs. But actually, you'll see what ends up happening is that this model ends up being useful in studying like Bernoulli matrices, independent Bernoulli matrices, right? So somehow, like what happened is we were studying directed graphs, and we were studying these models where the rows come from the slice, and that actually ends up being the correct thing to do to study the sharp invertibility of Bernoulli matrices as well. Okay, so yeah, this is as far as results go. Now I can tell you what the plan is for the rest of the talk. The plan is that first I want to give a self-contained proof of Conglocious result that the probability of singularity of a Bernoulli matrix goes to 0 as n goes to infinity. This will already sort of give a high-level overview of how things in this area might be proved. And after we have like a full proof of Conglocious result, I will talk a little bit about sharp invertibility and what kinds of modifications are. So that's the plan. But if there are any questions about what the results mean, I'm happy to stop here.
Just a quick question here. So do you get the same thing if you take a k slice?
Yeah, so it works for like a k slice if okay, so
p is
n over 2 can be
k
replaced
over
by np, where p is between 0 and 1 and p is fixed. Yeah, absolutely.
Okay.
Absolutely. Yeah. I mean, you can also like prove versions for like where p goes to 0 with n, or like p goes to 1 with n, but then you have to like do a little bit more work. And like personally, I have been like verified about that. But yeah, I mean, n over 2 is just sort of like for simplicity. Okay. Yeah, so now somehow as a warm-up, right? So you might say, okay, you have like a bunch of results. Now, how might I prove something of this form? So yeah, rather than just, so since we have like a little bit more time in the seminar, I thought that maybe I'll give you like a proof of Conglocious result. Okay, maybe this is not the proof that Conglocious had, but let's give like some proof of Conglocious result. And somehow, like what's been happening in the past 50 years is somehow, okay, there are like very obvious places where you can improve these arguments, and then in the past 50 years, it's just about like improving these arguments somehow, right? So there's like more and more machinery to do this thing. So yeah, so let me give you like a proof of Conglocious result on the singularity of n by n matrices, ID matrices. One thing is I was using like Bernoulli 1/2 last time in the first slide. Let me use Rademacher matrices just because it's slightly simpler. But at this level, there is no difference between Bernoulli and Rademacher. You can like reduce from one to the other, right? So there is some reduction that you can do. Okay, so let's talk about anti-concentration as a little bit of a problem. So this is like a very important idea in this area, and I think a lot of the development of little bit of a theory has been motivated by random matrix theory as well, especially the singularity and least singular value problems. Okay, so this is the problem posed by Littlewood and Offord in 1943. So okay, so you have like a bunch of non-zero integers. It can be anything, right? Like 5, 11, -2, something, right? And what you're doing is you're looking at a random walk, right? You're looking at a random walk where the magnitude of the steps are these numbers, right? Okay, so C1 through Cn are ID Rademacher random variables, and you're just looking at a random walk where the steps are A1 through An, right? So the first guy can be plus A1 or minus A1, the second guy can be plus A2 or minus A2, and then these steps are independent. And what you're asking is, what is the maximum value, or like, what's the maximum value of the probability of taking on any particular value? Okay, that was very confusing, but let me sort of say it here. So you have this random walk, and this random walk is valid in the integers, right? So for every integer, you can compute the probability that this random walk lands at this integer, right? And then you can maximize this probability over all of the integers. And then you're asking, well, how big can this maximum be, right? So this is let's call this the item probability. So what's the input here? So I give you the vector. So I give you the steps of the walk, and then I ask you, what's the largest probability of like taking, like, what's the largest point probability for this random, right? Okay. So maybe like let me do an example to clarify this definition. So so these are sort of two extreme examples here, right? So one thing that you can imagine is maybe my vector here, the steps of my walk are like 10, 100, 1,000, and so on. So what's going to happen is basically I'm getting some unique encoding of the walk here, right? I'm getting a unique encoding of my sign sequence, and since I have like 2 to the n sign sequences, and each of them is taking a different value, the probability of taking on any value is at most 2 to the minus n in the support, and then it's exactly 2 to the minus n for any point in the support, right? So this is one extreme, and this is the smallest that it can be just by pigeonhole, right? Because I have like 2 to the n guys, and one guy must have like at least, yeah. Okay. On the other extreme, since I've demanded that A1 through An be non-zero integers, you can ask, okay, let's say A is just like all ones. So this is my standard random walk, right? And now if half of my signs end up being 1 and half of them end up being -1, then I will land at 0. So the probability of being at 0 is n choose n over 2 times 2 to the minus n, right? So these are like some extreme situations here. And it's a theorem that these are the extreme situations. So let me discuss that. So yeah, so anyway, Littlewood and Offord, they were interested in like roots of random polynomials, and then this problem comes up there, and they wanted to study this thing. So they asked, okay, how large can this probability be? How large can the atom probability be? And then they showed that, okay, the atom probability is at most log n over root n. Okay, so this was like a theorem of Littlewood and Offord. And then Erdős famously showed that the example I showed you before, the all ones thing, is the extremal example, in the sense that the atom probability is at most n choose n over 2 over 2 to the n, right? So this is a tight example, and this is like a famous theorem of Erdős, right? Okay. So let me actually even show you the proof of this thing, because this is a combinatorial proof and it's rather short. Okay, so what do I want to show? So I want to show that the probability that the random walk equals x is at most n choose n over 2 over 2 to the n for any value of x. Okay, so let me fix x, and then I will just prove this uniform bound. Okay, so let's fix x. So x is an integer, 5, you can fix it. And I have this random walk a1 epsilon 1 plus a2 epsilon 2 plus an epsilon n. And since the Rademachers are symmetric, I can assume that AI is bigger than 0 for all I, right? The distribution is the same. You can replace AI by its absolute value, and the distribution of the random walk is going to stay the same. Okay. So here is Ardesh's insight. So he says, okay, let me look at let me look at some sign combination which gives me x, right? So some collection of plus ones and some collection of minus ones, which give me x, and let A be the set of the plus ones, right? So the sign sequence is completely specified by giving the set of plus ones. And Ardesh says, okay, list down all of the sign sequences which give you x, and then just like look at the set of all of the pluses, right? So I get like a bunch of sets, and this is in bijection with the sign sequences which give me x. So what's the key observation here? So the key observation here is that the collection of the sets is an anti-chain, right? The reason being that all of the AIs are positive. So if A1 is contained in A2, right, then A2 has pluses for every place where A1 is a plus. So the value for A2 must be larger than the value for A1, right? So it must land at something which is bigger than X. So A must be an anti-chain, like script A must be an anti-chain. And now by Sperner, I know that the maximum size of an anti-chain is at most n choose n over 2. So this tells me that A is at most n choose n over 2, and the probability of any sign sequence is q to the minus n. So this proves the inequality, right? So this is Ardesh's proof. I mean, it's really beautiful, like really like two-line proof, right? Okay. Yeah. So we will do like much harder anti-concentration results later.
Vishesh, actually, I have a quick question. Out of curiosity, do you have any idea how Littlewood and Offord managed to get their bound?
Yeah, that's a good question. Like honestly, you can imagine that I've never had any motivation for looking at their proof. But yeah. I should say that like all of the modern proofs are really just based on characteristic function arguments, right? So this is like somehow like a tailored proof, right? But now there are like, of course, like much more precise statements of this form. Okay, if you have like some more structure on A, so here it was only this thing that the entries of A are non-zero. Then you might ask, okay, let's say they're all distinct or something, right? And then all of these proofs are Fourier-related. So but from at least to my knowledge, the person who introduced the Fourier or the person to whom the Fourier analytic approach to anti-concentration is attributed is Assine. So Assine has like a famous paper from like I think the 70s, where he had like a proof of unifying sort of many of these things. So yeah, I don't really know how Littlewood and Offord proved this time. Yeah, I mean it's a good question. It's something to look at. Yeah.
Thanks. Yep. Thanks, Vishesh.
Yep. But yeah, so this is Ardesh's proof, and yeah, this is like really like the book proof of this inequality. Right. So okay, cool. Yeah, this is going to be like the last anti-concentration inequality I prove, but I will skate more things. Okay, cool. So what good is this, and how is this connected to the problem at hand? Okay, so that's kind of unclear right now, but this was some I hope interesting diversion. So let's see how this is connected to the problem. So let's sort of see how we might prove Conglocious theorem, and this again template is going to be followed for the rest of the proofs. Okay, so now you might say, okay, suppose I could prove. So I'm going to maybe use the word structure theorem again. So let me just call a statement like this a structure theorem. So okay, so I have like an n by n Rademacher matrix, right? Let's say I could prove some sort of preliminary structure theorem about its kernel, which is the following. Suppose I could show that with high probability. Okay, in this case, it doesn't really matter that it's very high probability. It's fine if it's like probability going to 0 as n goes to infinity. But suppose I could show that with high probability, any non-zero left or right null vector of my matrix has many non-zero entries, right? Okay, like linearly many non-zero entries. And now you see that, okay, this is like somehow connected to the Littlewood-Offord problem, and that's where the connection is going to be. Okay, but suppose we could prove something like this, and later I will show you how to prove this thing. But suppose we could show this thing. What good is a statement of this one? Okay. Okay, so let's try to think about if we had this magic statement, what could we do? So let's do a little bit of linear algebra. So let's say E is this event. E is this nice event where I know that any non-zero left or right null vector of my matrix has linearly many non-zero entries. And let's see what I can do with it. Okay, so I denote the rows of my matrix by R1 through Rn, and then Si is the event that Ri lies in the span of the other rows, right? Okay, so if my matrix is singular, then at least one of these guys must count. Okay, the key observation is that if my matrix is singular and the event E holds, then at least n over 100 of these guys must hold, right? Because any like left null vector, right? So if my matrix is singular and the event E holds, then it must have a non-trivial left null vector. But any left null vector has n over 100 non-zero entries. So there are at least n over 100 rows which are in the span of the remaining rows, right? So there are like at least n over 100 events that hold on the right-hand side. So I can put like an n over 100 on the left-hand side here. Okay, right? So this is just saying that this guy, like if the matrix is singular and E holds, then let's say row 1 is in the span of the other rows, row 5 is in the span of the other rows, and so on for like n over 100 of these things. And now what I can do is I can just take expectations on both sides. So if I take expectations on both sides and use the law of total probability, okay, so the probability of the singularity is the probability of S intersect E plus the probability of E complement, or at most the probability of S intersect E plus probability of E complement. So this I will bound later. And the probability of S intersect E, so all of these probabilities are the same by symmetry, right? Because the rows are symmetric. So the probability of S1 being in the span of the other guys is the same as the probability of Sn being in the span of the other guys. So this probability, the expectation of the right-hand side, for instance, is just n times the probability of Sn intersect E, and then you can cancel the n's on both sides, right? So this is just saying that, okay, the probability of singularity is bounded by the probability of the complement of the structure event, which I hope is close to 0, and the probability that, let's say, the last row is in the span of the first n minus 1 rows, given that this good event E holds, right? And now this good event E is saying something about possible normal vectors. So the hope is that, okay, I will be able to use some anti-concentration here, and then anti-concentration, I mean like a little bit of a result, and then this I will like try to bound separately, right? So this is the basic linear algebraic reduction, and I will show you sort of like how to do both of these pieces. But are there any questions about this step before I proceed? Okay. Okay. So if not, so let's just sort of do this thing. Okay. So now what am I going to do? So on the next slide, I'm going to try to bound this term, probability of Sn and E. Okay. So okay. So what is the thing I'm trying to bound? I'm trying to bound the probability that the last row is in the span of the first n minus 1 rows. Yeah, and I have and I know that I'm on this good structured event E, where every left or right null non-trivial vector, every non-trivial left or right null vector has linearly many non-zero entries. Okay, so the idea is what I'm going to do is I'm first going to expose the first n minus 1 rows. Then I will use this will give me a normal vector to a hyperplane, and then I will see what's the probability that the last row is perpendicular to this normal vector. Okay, so let's say n is a vector which is perpendicular to the first n minus 1 rows. So there is some vector, and let's say I can fix one arbitrarily by like having a fixed map from every hyperplane to a normal vector. Okay, so if the last row is in the span of the first n minus 1 rows, then it better be the case that the last row is perpendicular to it. Okay, so let's do some case analysis and see what can happen. So I have two cases here. So one case is that n has fewer than n over 100 non-zero entries. Well, if n has fewer than n over 100 non-zero entries, then it cannot be the case that Rn is perpendicular to n, because then n would be a right null vector with fewer than n over 100 non-zero entries, which cannot happen on my event. Okay, so this is gone on my event E. So it must be the case that n has at least n over 100 non-zero entries, right? But if n has at least n over 100 non-zero entries, and I can assume that it's an integer vector because right, like if my matrix is singular, it's singular over the rationals, and then I can clear out denominators and say singular over the integers. So n is some integer vector with at least n over 100 non-zero entries. The probability that Rn is orthogonal to n is exactly the probability that the random walk, whose coefficients are n, is 0. And by the Littlewood-Alford inequality, by the Littlewood-Alford inequality, the probability of this happening is at most 10 to the minus 1/2, right? So if you put this Q together with the law of total probability, this shows that the probability that the last row is in the span of the first n minus 1 rows on the event E is at most 10 to the minus 1. Okay, so this takes care of my first term, and this is sort of the leading order term in this argument. And now what I want to show you is that E is going to happen with high probability, so I can bound the probability of E confidence, right? But here is sort of like how the Littlewood-Alford theory is used. The idea is that, okay, I prove some statement about potential kernel vectors, right? And then I keep one row, the randomness in one row free, and then I can sort of use my thing. So that's the idea. And now I'll show how to prove the statement that any potential null vector must have at least n over 100 non-zero vectors. Okay. So let's go there. Yeah. Okay. So now I want to prove the structure theorem, which is that any non-trivial null vector has at least n over 100 non-zero entries. Okay. And it's fine for me to like prove it with probability little o n 1 here, but actually we'll prove it with probability that's exponentially small. Okay. So let's see how to do this thing. So now you might say, okay, let me look at a fixed vector. Let me look at a fixed non-zero vector and ask what's the probability that this vector is a null vector of the matrix, right? So this is at most q to the minus n. So what you can do is you can say, well, since v is a non-zero vector, let's say v1 is not equal to 0, and then for every row you can expose all of the entries except for the first one, and then there is at most one choice of the first entry that's going to make that row 0, right? So there is a probability of at most 1/2 for every row, and the rows are independent. So the probability that v not equal 0 is a null vector of Mn is at most 1/2 to the n. And now you might ask, okay, can I just use the union bound? It doesn't really make sense. Can I just use the union bound? There are like infinitely many vectors. So what am I doing a union bound over? Okay, so here's a trick that I learned from Asaf Ferber, right? So he said, okay, so for instance, if I view the vectors, okay, so firstly, if my matrix is singular, it's singular over the rationals, right? And by clearing denominators, I can just assume that I only need to care about null vectors which have integer entries. So Asaf's idea was that, okay, for instance, I can just prove this statement instead of over the integers or rationals. I can prove this statement over f3 to the n, and then this is going to imply the statement that I want, right? So let's think about this for a moment. So what do I want to show? I want to show that any vector with at least 99 n over 100 zero entries cannot be a null vector over the integers, for instance, right? Over the rational numbers. And if you could show this over f3, this also implies this over the rational numbers or the integers, right? Because if something is 0 for f3, if something is 0 in the integers, then it's also 0 in f3. And if the equation holds over the integers, then it also holds over f3. Right? So this is fine. So this is a stronger statement. But now you can use the union bound, right? Because now you might ask, okay, how many vectors do I have over f3 to the n with at least 99 n over 100 zero entries? Well, it's n choose n over 100. I need to like pick the non-zero entries, and for the non-zero entries, I have two options. So it's like it's 2 to the n over 100 over times n choose n over 100, and then okay n because it's at least 99 n over 100 zero entries, right? So it can sort of go up. So maybe there's some factor here. But in any case, if you do this computation, it's like much less than 2 to the n over 2. It's less than 2 to the n over 3, or like 2 to the n over like 99 or something, right? Okay, so it's much smaller. And now, so this statement is also true over f3, right? Because you can do the same argument of, let's say v1 is non-zero over f3, and then you can expose the rest of the row, and the probability that the dot product is 0 is at most 1/2. So this thing is still true. So the probability of any vector being the null vector is 2 to the minus n. And I need to worry about at most, let's say, 2 to the n over 2 null vectors, right? These are the bad ones. And now I can do a union bound. And this shows that with the probability of this event E holding is 1 minus some exponentially small term, right? So indeed, the structure event is true. And now I can use the Littlewood-Alford reduction. And now I can like complete my proof, right? So at this point, I haven't like hidden anything from you. And this is like really a full proof of Conglocious result. And now you can kind of imagine what's going to happen here. So if you step back and think about what happened here, we had something here. And this thing we said is exponentially small, like 2 to the minus n over 2 or something. And this thing was like 1 over root n, right? So now what we want to do is somehow we want to like prove a much more precise little bit of a result, which is going to change the 1 over root n here to the correct answer. And then we want to prove a structured theorem which enables us to use that kind of anti-constitution, right? So this is where things are going, but it's still going to be this sort of like general high-level framework. So I hope that even if you don't follow the rest of the talk, there is like one proof that you could reproduce if you were asked to, right? Okay, yeah. So let me stop here and see if there are any questions. And if you want, I can either take a short break here, or I can proceed, which is also fine with me.
So Vishesh, I have so this very nice argument about using f3 to the n made me think. So the same proof, would it show that we actually can get the same bound over f3 to the n?
Yeah,
like
yeah,
if you
yeah,
ask.
So yeah. So you can,
and what's the state? Was this problem studied for finite fields as well? Is it the same conjecture that the?
Well, okay. So what? No. So what this thing shows is that the structure theorem is true over f3 to the n, right? But that's not the same as saying that the singularity probability over f3 to the n is like, because if you think about it, right? Like for anti-concentration over like f3, there is like some value that's going to be taken on with probability 1 over 3, right?
Yeah.
So you can't really use that. Now,
is there a way to?
Now, so this problem has been studied over finite fields as well. And over finite fields, you can actually even do like quite exact things, right? So in terms of references, there is a paper by Kenneth Maples, which actually does like quite exact statements here, right? So you can like actually write down in quite an exact form what the probability of singularity is over finite fields, and it actually turns out to be okay. So you can ask sort of like two questions, right? One is you can fix the size of the field and then have n go to infinity. And the other one is that maybe the size of the field could also be increasing with that, right? So as long as the size of the field is, let's say, up to some small exponential in n, you can actually prove very precise results. But then you can imagine that if the size of the field gets much larger, then at some point you start losing the distinction between working over the integers and working over like a large field, because the problem over the integers, you can like embed this into like a large enough field, and then it's equivalent, right? So at some point it becomes like as hard as studying this problem. But for size of the field up to a small exponential, you can actually prove very precise results. And this is done in a paper of Kenneth Maples, actually using the same techniques as Conglocious Theorem. Right.
Okay.
So
okay. But it still does it decrease exponentially also? It should like decrease. Or I don't know actually.
No. Right? No.
No. Okay.
Yeah. No.
And this proof, like there is no way to fix the first part so that it works. Like an easy way to fix this first part so that it works for the finite field case.
Okay. So in the finite field case, the truth itself is not this thing, right? I think you should get like a 1 over q kind of thing, like 1 over p kind of thing, I think. Okay. And you can indeed prove something of that form. Actually, like quite exact things. Yeah.
Okay. Okay, thanks. And as for the break, I don't know. I'm fine with continuing.
Yeah. Okay. So we have some momentum, I guess, and maybe we come back and we've forgotten everything. So let me keep going. Okay. So let me say something about the strong invertibility of discrete random matrices, right? And the template is going to be similar. Okay. So I want to do this thing, and let me just focus on the case of sparse Bernoulli matrices, right, where the dominant contribution is from a 0 row or column, and I will say like maybe like 2 sentences about what the changes needed to sort of do the general case, but most of the important ideas are already here, right? So I think if you sort of understand this proof correctly, then going from here to sort of general discrete random variables, okay, it does require some work, but it's the ideas I hope should be like, somewhat clear. Okay. Okay. So now there's going to be this thing. If you remember, I mentioned this problem about the singularity of random matrices where the rows are sampled from a slice, and now I'll say something about why that plays a role here, why that's useful. So here what I'm doing is firstly, let me just generalize this notion of like atom probability from before, right? So now it's sort of the same setup. So V is my vector of coefficients, C is like a random vector. Earlier, I was asking what's the probability of this random walk taking on a particular value. But now we sort of like allow ourselves a little bit more room, and we fix a radius R here. And it's okay, what's sort of the most probability of lying in any given ball of radius at most R, right? Okay, so now this is sort of this is like a generalization. Previously, we were working with the case R equals 0. Now I'll work with a positive R. Also, previously, I was working with the case where the random variables and the random walk are all independent. But now, okay, so now the things I care about will be either the case where they are like Bernoulli P, so that's fine, that makes sense because that's what the problem is about, or they are uniformly distributed on the slice, right? So I'm sampling the whole row from the slice, and I'll say in a minute why this is useful. Okay, so let's just give some examples of this thing that we've seen before. So it's exactly the same thing. So let's say V is all one, and now I've chosen the radius to be small enough so that taking on a particular value is the same as lying in this interval, right? Okay, so the behavior we've seen these things, right? The behavior is the same. So if V is the all ones vector, then the probability of taking on any particular value is at most 1 over root n, right? Order 1 over root n. So this is like some generalization of like Erdős bound. If V is completely unstructured, so all of the entries of the walk are going to land up in unique values, right? So now you might say, okay, if I have a Bernoulli P, what's the most likely value that I'm going to take? Well, the most likely value is for each guy to be 0, right? So the most likely value is for each guy to be 0, each random variable to be 0, and correspondingly for the sum to be 0. And this happens with probability 1 minus p to the n, right? So this is fine. So now let's think about this for the moment. So now let me ask the same question. So V is this guy, right? Where everything is going to unique value. But now instead of sampling things from the Bernoulli distribution, right, like the product of Bernoulli P's, I'm sampling it from the typical slice, right? So if I have like Bernoulli P's, then the typical value of the sum is Pn. So now let's say I condition on the sum being Pn, for instance, and I'm sampling from the slice NPn, right? So the sum of the plus ones is Pn, right? And now let me ask, okay, what is the anti-concentration date? What's the most likely value, right? So now it's more interesting because I have like n choose Pn values in this slice, and each of them is mapped to a different value, right? Because I have a unique encoding here because of the gap between my coefficients. It's like some Bayesian expansion. So I have like n choose Pn values. Each of them is taken on with the same probability. So the probability of taking on any value is at most 1 over n choose Pn, right? The thing that's important is that for p which is between 0 and 1/2, or let's say p which is not equal to a half, or p which is between 0 and 1/2, n choose Pn inverse is exponentially smaller than 1 minus p to the n, right? So what's happening is that, okay, when I look at, so I have this problem with Bernoulli random variables, right? But I have n rows, and most of them are actually going to look like this thing, right? So by Chernoff, I know that there are maybe constantly many rows which will deviate from n choose Pn by like some small amount, like p plus minus epsilon n. So most of the other rows are actually going to be drawn from these well-conditioned slices. And on these well-conditioned slices, I actually have some exponential gain over just using Bernoulli concentration, right? So this is sort of why working on the slice is an advantage compared to working with the independent version, because you get improved concentration. And now I have this sort of exponential room that I'm going to exploit. This also shows why we cannot handle the case p equals 1/2, because if p equals 1/2, then the gap between 1/2 to the n and n choose n over 2 to the n, it's like a polynomial, right? And really, like, the arguments that we have lead to some exponential loss. So having this exponential room is very important, right? So this is sort of the one-line summary of why working on the slice is important and why we need to work with non-uniform distributions, right? So yeah, this is sort of one thing. I mean, in general, you can ask, okay, if P is bigger than the half, we can still prove the result. And then you have to sort of like think about the correct thing, right? So in that case, you would be comparing it to the probability of having a row or two rows being the same, for instance, and then that's like P squared plus 1 minus P squared to the end, right? So you will have like an inequality of this one. Okay. Yeah. So this is sort of like why this slice is important. Okay. So now let me say a little bit more. So this is the anti-concentration part. Another thing that we do. So I've been saying a lot about singularity, right? But what actually happens in this proof and in like many of these proofs is instead of the singularity probability, you actually just control the tail of the small singular, right? Okay. So let me remind you what the singular value of a matrix is. The smallest singular value of a matrix is. So you look at the unit sphere, right? And the unit sphere is mapped to some ellipsoid onto the matrix. And then you're asking what's the closest point to the origin for this ellipsoid, right? So that's the length of that point is the smallest singular value. And right, Mn being singular is the same as the smallest singular value being 0. But actually, what will happen is that we'll end up controlling the tail of the smallest singular value. Okay, so firstly, this is how the proof goes, but also controlling the. I mean, okay, so in this case, we like the whole point is to prove the result about the singularity and to understand why the matrices are singular. But generally, controlling the tail of the singular value is more important than like bounding the singularity probability for many applications. And this is, I guess, how the field really started. So I think von Neumann and Goldstein were interested in the condition number of random matrices, and they really sort of started studying this problem. Okay. So this is just some byproduct that, okay, I will actually just control the smallest singular value, which is the optimization problem. It's some optimization problem of this field. Okay. And the final sort of general remark. So previously, if you think about like how we handled our problem, it was somehow by splitting all possible vectors into two cases, vectors which have like very few non-zero entries, and then vectors which have like many non-zero entries, right? So something analogous is going to happen here, except it necessarily has to be more complicated. And now I will just think about decomposing this here, right? So I want to show that the infimum of some random quantity, right? So I have like something indexed by vectors of the sphere is large. And the way I will do this is by breaking the sphere into a bunch of parts and then analyzing those parts separately. Okay. So what are going to be the parts here? So one part is going to be vectors which are like almost constant. So in the sense that they have 1 minus delta n of their coordinates within like a small constant times root n, 1 over root n of each other. Okay, so what's the reason for this thing? Well, okay, so previously we had, okay, let me actually go back here. So previously, the thing that we were thinking about was non-zero vectors, or like vectors with many non-zero entries. The reason being that if I have like a zero vector, for instance, then it has no anti-concentration, right, for like Rademacher's. Okay. Here, if you're working on the slice, then having a lot of non-zero entries is not enough, because if you think about the all ones vector, then it's always going to map to Pn, right? So the thing that's actually important is being far from a constant vector, and that's why the analog of sort of vectors with many non-zero entries in the Rademacher case is vectors which are far from being constant vectors, right? So that's why we have to look at that piece. Within these vectors, we have to isolate vectors which are close to being elementary vectors, and I'll say that in a moment why. And then you have to sort of think about the remainder of the piece. So this was sort of our analog of vectors which had like many non-zero entries, and here it's a more complicated piece. Okay, so let me just say why we have to isolate these elementary vectors. So recall that the goal here is to say something about the sharp invertibility of random matrices, right, of Bernoulli matrices. And here the leading contribution is really going to come from the vectors E1 or E1 transpose or something of this form, right? Because a column being 0 is the same as E1 being, like the first column being 0 is the same as E1 being a right null vector, right? Or like the first row being 0 is the same as like E1 transpose being, or like E1 being E1 transpose being a left null vector. So since these guys like are playing a role, you clearly have to handle them separately. And if you only care about the log of the probability, then you don't really have to like do the separate analysis. You can just break things into like constant and non-constant, right? So that's sort of the idea. So here, because you kind of have to like think about the leading term, you must analyze it separately, right? Okay, so that's one thing. Okay, so there are like these pieces here. So you have constant vectors. Within constant, you have these elementary vectors, and then outside of the constant vectors, you have these non-constant vectors, right? So going to analyze these step by step. Okay, Andrew, you have a question?
Vishesh, yeah, maybe I don't know, a stupid question. So in the anti-concentration setting, so is there a quick way to see why you would so the intuition for this vector around which you want the sums to concentrate. So what was it in the previous kind of? Yeah, I'm just so this Z that you have here.
You mean Xi?
Like.
Oh, you mean the Z? Oh, yeah. Okay. Yeah. So I mean, the thing is that.
Yeah. So.
Okay. So in the previous case that we were thinking about, right? Like the Z that you care about is 0, right?
Yeah.
But the thing is, like the way you prove these bounds, they actually just you actually end up proving a uniform bound anyway, right? Like there is like some sort of triangle inequality that you do, in which case the phase information disappears anyway. So it's nice to have this additional flexibility actually. Like there are like some places where it's nice to have the flexibility of like arbitrary points. But like for instance, in the previous argument I showed you, the Z that we cared about was really only 0.
Yeah. This is why I was. So it's okay. So it's more.
But you can think about like if you do like some sort of symmetrization argument, right? Then Z equals 0 is like the most likely thing if you do up to like some symmetrization argument. You don't like really gain anything more by saying that, oh, there is like only like some small class of Z's I care about, because the Z that you care about is like the worst case Z anyway. Yeah, but that's a fantastic question. Yeah. So you might ask, okay, can I, instead of working with the uniform anti-concentration function, can I do something better by tailoring it to like certain choices of Z? And in this case, no, because the choice of Z you care about happens to coincide with the worst choice anyway, essentially. Okay, but fantastic question. Okay, so there is like one part here which is genuinely easy, which is the constant vectors, which are not elementary vectors, right? So I have these constant vectors, within them elementary vectors, and then the complement of the elementary vectors within the constant vectors. This is just something which is like genuinely easy to handle. And this you can just sort of do by some standard argument. So let me not even like spend too much time and just sort of say how you do this thing. So the idea is that if you have a vector which is not elementary, so which is far from being like E1, E2, En, then the anti-concentration for Bernoulli P on this thing is a little bit better than 1 minus P, right? So think about this. So in general, right, like if I give you the vector E1, then I only have one random variable here, and it's going to be 0 with probability 1 minus P, right? So I cannot do better than that. But if my vector is far from elementary, then I can do a little bit better. And okay, there's like a couple of ways of proving this thing. I mean, okay, there's like a way of proving this thing, which is do some sort of case analysis. Yeah, let me not even go into that too much, but this is, believe me, this is like a genuinely elementary argument that you can show. And once you have this thing, okay, then you know that the anti-concentration on these vectors, on any vector which is not elementary, is a little bit better than 1 minus P. And now you can sort of combine this with the union bound argument for these constant vectors to show that, okay, for vectors which are constant but not elementary, I have a contribution which is 1 minus P to the n times some exponentially small term. So I can just sort of like dispense with this part, right? So this is some part which is like not very interesting, and this can really be handled by separate methods. So what's the idea here? So the idea here is that a vector which is not elementary has better concentration than elementary vectors, because these are sort of like tight for the analysis. And now remember, we had this argument where we did like a union bound, right? Over vectors with a few non-zero entries. So now you do like a similar sort of argument like this thing. You say, well, okay, if I have a vector which is almost constant, then clearly like there are like a small number of such vectors, right? In the sense that I can construct a small epsilon net, right? I can construct like an epsilon net of small size with like a suitable epsilon, and then you can like really just do the union bound argument, and you can make this argument go through, right? So that's what I mean by low metric entropy. That constant vectors are few, And for these guys, I have like good enough anti-concentration that the argument goes through. Okay, let me move to like some more interesting pieces. But if somebody is very interested here, I can of course take the question. Okay. Yeah, this is like the kind of argument we've seen before. Okay, so now the other thing, the next part we analyze, which is still like something that is not super hard once you have the correct reduction, is elementary vectors, right? And now, for instance, what you want to show is a statement of the form that the probability that the infimum over, let's say, elementary 1 vectors, so vectors which are like very close to E1, being, let's say, exponentially small, I mean, we really care about 0, but let's say exponentially small, is 1 minus Pn plus some like lower order thing. And the point is that when I do this over all n elementary vectors on the right, then it's going to give me a term n1 minus p to the n. And then when I do the transpose, right, so like ymn, then it's going to give me another n, and this is going to be the leading order term, right? So this is what we do. Yeah, let me actually show you the reduction because, okay, yeah, how am I doing on time, by the way, Andre? I think I've done an hour, right? Hour, 2 minutes.
Yeah, it's you've done an hour, yeah. So
okay.
You have a lot of time.
Okay, cool. Okay. So let me sort of show you what the reduction here is, right? And this is still not bad. Okay. So since I'm working with elementary 1, and since I'm thinking about right null vectors, let me isolate the first column and the rest of the columns, right? So I denote the first column by m1, and I denote the rest of the columns by n minus 1. So n minus 1 is some n by n minus 1 matrix, right? Okay. So let's like do a thought experiment and see what happens. So let's say I have a vector which is an elementary vector, which also has like a very small image under my matrix, right? So okay, I'm looking at unit vectors here, but right, like I can slightly normalize everything because there's like an exponentially small factor here. So let's say my vector is of the form.
Vishesh, sorry, can I ask a quick question? Yep. So this in the notation, this elementary 1, so 1 is the number of the support of the vector that it's close to the size. And c, so okay, it's distance at certain distance, so it depends on this p and rho p and c, right?
Yep.
And this so p was this distance or rho p, and c.
Okay, this is rather confusing. Yeah, sorry. Let me actually say this more precisely. So c is like some number which is fixed. Let's say c is 1/2, right?
Okay.
If you prove it for 1/2, you're fine. What is p? So p is the bias of the Bernoulli.
Yeah.
So p is the bias of the Bernoulli, and c is some number. So these two numbers are fixed. And now, what is the point? So elementary 1 means that let's say it's within distance rho of the vector 1, 0, 0, 0, 0.
Yeah. Okay. So rho of p and c, it's some function that
it's some function which depends on p and c.
P and c. Okay.
If you fix p and you fix c, then it's fixed. And then it's saying that it's like within distance rho of E1, and up to some slight normalization. The fact that it's on the sphere. One way that you can think about this vector is that this vector is E1, right? So 1, 0, 0, 0, plus some vector supported on the other n minus 1 coordinates, which has norm at most rho. Okay. I'm cheating a little bit because I should divide the whole thing by like 1 plus rho or something, or like 1 plus rho square root. But yeah.
But now I see it.
Yeah. Okay. Right. Okay. So let's say that x is a vector of this form, which is 1 in the first coordinate, and the last n minus 1 coordinates have norm rho, and this gives me very small image under my matrix, and then let's see what I can say. Okay. So so J is like the all ones matrix, right? It's like a matrix, n by n matrix, which is like 1 everywhere. So if you do some like manipulation, this is the upshot that you have. Okay, so what did I do here? So I just like literally wrote down m1 plus p times j times u. U is this guy, and p is the bias of the Bernoulli, and j is the all ones matrix. This is very unmotivated right now, but let me just sort of like actually do this thing and see what the upshot is. Okay, so the upshot is the following. So if you think about M1, right? Yeah, so if you think about M1, this is like a random, it's a random column, that's a random vector with 0 with probability 1 minus p and p with probability 1. So it has norm like about root m, right? Like up to like some constant depending on p. Okay. What this thing is showing is that if something like this is true, like if it is the case that a vector, which is like an elementary vector, has very small image, then the first column must be very close to a constant vector, right? So Ju is a constant vector, right? Because it's the all ones matrix, so everything is going to be the same. So Pju is some constant vector, and what this is saying is that okay, if like this thing happens, which is bad for me, then at least I have some structural information about the first column, which is that the first column must be very close to a constant vector, right? Okay. So this is the upshot, and you can prove this using the triangle inequality in like some manipulation, which is not super interesting. Okay. So what's the upshot? Okay. So the upshot is that M1 is very close to a constant vector. Okay. Why is this useful for me? So now you can do some case analysis here, right? So you can say, okay, I know that M1 is an integer vector, right? It's like the entries are 0 or 1. And now it's also close to a constant vector. So it could be like very close to 0, or it could be like very close to 1. Okay. All 0 or all 1, these are like the two constant vectors, and it's like very close. Okay. So one case is that, okay, M1 could literally be 0, right? This happens with probability 1 minus p to the n, and this is like the dominant term, right? This is sort of like a thing, because if M1 equals 0, this genuinely means that my matrix is singular. So this is unavoidable, and this is going to lead to the 1 minus p to the n term. Okay. Now you can say, okay, if M1 is not 0, I know that it's close to a constant vector, and it's either close to like the all 0 vector, or it's close to the all 1 vector, right? And because the probability of p is the dominant one, right? It's exponentially more likely to be close to the all zeros vector than to be close to the all ones vector. Okay. So the probability of being an almost constant vector is 1 minus p to the n, which is the probability of being all zeros, plus some small exponential term, which depends on the distance to account for like the choices, right? Like the level sets, okay, the size of the level set. Okay. So I know that, okay, M1 is so now I'm in a good position, because now I know that the probability of getting such an M1 is 1 minus p to the n times some small exponential term. Okay, this is still not great for me, because what I want is I want to bound the contribution of this thing by 1 minus p to the n times e to the minus epsilon n. But now I know that the number of these guys is 1 minus p to the n times e to the plus epsilon, right? So something. Okay. But now this is something about M1, and so far I haven't really used the randomness of the other part of the matrix. So and I also haven't really used the fact that the image of x under M1 under the matrix is exponentially small, because if you sort of go here, the only thing I'm using is that the image m and x is like little o square root n, and this is already enough for this argument. So I must somehow use the fact that the image is like exponentially small. And now I'm going to use this thing. Okay. So now I say, okay, now I'm just going to do like a union bound over this thing, a union bound. So let's say a condition on the choice of M1 not equal 0, right? I condition on the choice of M1 not equal 0, and it's an integer vector, so the norm is at least 1. Okay. So now I fix the first column, and the first column is some vector, some integer vector, which is at least 1. And now I forget about the fact that it's constant, non-constant. I don't care. The only thing that I was using about the fact of it being close to a constant is that the probability of this thing is 1 minus p to the n times e to the plus epsilon. But now let's say I just think about some vector of norm bigger than 1, and I know that m and x is exponentially small. And if I just write down what m and x is, it's just like the first column plus m minus 1 times u, right? Where u is like some vector. So remember, x was e1 plus u. U was only supported on the last n minus 1 coordinates. So m minus 1 exactly sees u, and m1 sees e1. So this is exactly m and x. And this I know is exponentially small. Okay, so now if you think about it, what's going on here, right? So m1 is some fixed vector. M minus 1 is an n times n minus 1 matrix. So its image is going to be some random n minus 1 subspace, n minus 1 dimensional subspace, some random hyperplane. And now you're saying, well, I have a fixed vector, and I have a random hyperplane, and this random hyperplane is exponentially close to my vector, right? So this thing is very unlikely. And this is like a result essentially of Rudolphson and Verschinen, that if you fix a direction, right? So if you fix a vector, then I have like an n minus 1 times n. Okay, I have some n minus 1 dimensional subspace. And okay, if you assume that, for instance, this matrix is Gaussian, then it's like really a uniform subspace, right? It's like really a uniformly random subspace. In this case, okay, it's Bernoulli. It's not really uniformly random. It doesn't have to be. But the heuristic is it's kind of close enough to that. And at least for our purposes, we only want a very crude statement, which is that if I fix a direction, then there is no reason why this direction should be basically captured by my co-dimension 1 subspace. And this shows that the probability of this thing over m minus 1 is exponentially small. And then if you choose parameters correctly, then this exponential is, let's say, twice this exponential. So you can like do everything, and then this goes up. Right? So this is how you handle elementary vectors. And yeah, this is sort of like, this takes care of like two parts of the sphere, the elementary vectors, and then the constant vectors, which are not the elementary vectors. And now somehow we've done some amount of work, which might even seem a lot of work. And now we have almost the whole sphere left to still handle, right? So now we are going to do this thing, but are there any questions about this part?
So here, when you say exponentially close, you mean just the distance of like the orthogonal component is okay.
Like literally, like there is like so there is something in the image of m minus 1, which is like extremely close to m1. Right?
Mm-hmm.
So
the scalar product is extremely close to 1. So.
Yeah, in this case, yeah, exactly, okay. Exactly. Okay. Right. So there is like there's like no reason for it to be like this. Okay. Yeah. Okay. Okay. So what have we been able to do so far? So far we've been able to show that. So I have this optimization problem over the sphere, and I've been able to correctly control the infimum, the probability that the infimum over almost constant vectors, either on the left or right, is exponentially small. Right. So this I've been able to control. And what do I mean by correctly control? It means, okay, the probability of this thing is like 2n 1 minus p to the n plus 1 minus p to the n times some exponentially small term. Okay. So what do I want to do? So now I want to control the infimum. So both of these infima over vectors which are not almost constant. But now I can assume that I have this condition, right? So this is like, again, somehow similar to the thing we had before in Conglocious proof, which is you have like some information about the left and right null vectors, and now you want to like say something about that, right? But unfortunately, we won't be done in just one step here. This is just somehow the beginning, and you kind of have to like build up all the way over time. So I'll talk about what to do, but this is the problem. Okay, so now what I'm going to do is I'm just going to do like a bunch of linear algebra, and it's going to be very similar to the linear algebra we've seen before, which is to sort of somehow reduce this problem to an anti-concentration, a little bit of a problem, and then I'll just sort of discuss a little bit about how that problem is resolved and what the point is. Okay, so this is going to be very similar, right? So yeah, so I want to control the infima over non-constant vectors, right? And I'm going to use same notation as before. So let's say the rows of my matrix are R1 through Rn, and let's say the span of all rows except the ith row is denoted by hi, right? So H stands for hyperplane here, right? It's generically a hyperplane. And now you might say, okay, what's let's say ymn, right? So now I'm multiplying on y for whatever reason, but it'll be clear. So let's say ymn is just exactly this thing, y1 r1 plus yn rn. And this is at least this thing, right? So it's at least like one term here. So it's the distance of ri to hi times the size of yi. Okay. So this is true for like all i's. So in particular, it's true for the maximum. And now sort of the most basic version is, okay, this is the quantity I want to control, right? I want to control, okay, what's the point here? So the point is I want to control the infimum of this quantity over all y's. And what I want to do is, it's really hard for me to sort of work over all y's. So I want to do something like before, which is to just work with the distance of rows to the space spanned by the other rows, right? So that's the kind of reduction that I'm hoping for here. And the point is that, okay, there is at least one coordinate yi, which has value at least 1 over square root n, right? So if you do a union bound, it shows that the probability that the infimum here over the sphere is less than or equal to eta can be bounded by the sum of these guys here, right? And the point is that, see, this is like a complicated quantity over the sphere, right? This is like something which involves all vectors over the sphere. But now this just comes down to understanding the distance of one row from the remaining rows, right? So this is like exactly the kind of quantity we had before. Again, the reduction is you literally write this thing, and then you say that, okay, at least one coordinate is 1 over square root n. So if this guy is less than eta, and let's say the first coordinate has value 1 over square root, value at least 1 over square root n, then distance of R1 to H1 must be at most eta squared. Right? So this is sort of the basic version of the argument. Now, this is we've actually seen something a little bit more advanced already, which is the following. If we restrict the infima not to the whole sphere, but to these non-constant vectors, then you can like gain a little bit in the average, right? And this is like the thing we had before, where we said that, oh, if I know that my left or right null vectors have n over 100 non-zero entries, then there are going to be n over 100 non-redundant rows, and I gain a factor. Right? So it's exactly the same kind of argument. The idea being that if I have a vector which is not constant, or which is far away from being constant, then you can show that there are at least linearly many indices which are order 1 over square root n. So yeah, you can. So if you choose like a random index, there is like a probability 1 over delta that it's a good index, and then you can sort of gain in the union bound, right? Somehow this event is like a delta and covering of the other event, so you can gain a factor of 1 over delta. And in the probabilities, this is exactly analogous to the argument we've seen before for Conglocious, right? So this was important. Yeah, I mean, somehow like in the Conglocious case, this was really important because without this factor of n, we would be lost. Our anti-concentration was only on the level of 1 over square root n, so we could not really afford to multiply 1 over square root n by n. But you can imagine that, okay, if you had like better bounds here, this kind of thing is not important. But again, like in our case, this will be useful. Okay, so let me sort of go ahead and say a slightly more refined version of this thing. So the more refined version of this thing that we will need, and this is due to Tikhomarov and Litvak, is sort of like working on the slice, right? So let me sort of write the whole thing down and say here. Okay. So forget about like this epsilon I, and previously we had this version, right, just by linear algebra. And now what is the point? The point is that, okay, I can also just like assume, right, like in this event, I can also assume that my rows live in this well-conditioned slice, right? The reason being that by Chernoff, I know that the probability that this guy does not hold for a given row is okay. So I know that the probability that this guy does not hold for a given row is exponential in, let's say, gamma n, right? And if I take enough rows, right? So if I take a constant number of rows, right, where the constant depends on gamma, then Chernoff shows that with probability at most 100 to the minus n, for instance, the number of rows for which this thing is not going to hold is some constant depending on gamma, right? So there are so now if I think about what's going on, initially I was caring about the yi's which have value at least 1 over square root n, or like some constant over square root n. So I know that there are linearly many of these, and then there are like constantly many i's which are bad, so I can forget about those. And for everything else, I know that the distance is going to be eta square root n, and this condition ei is going to hold, right? So up to like losing this factor of 100 to the minus n, I've gotten myself to the slice. And now the point is that anti-concentration on the slice is better than anti-concentration on the cube, on the biased cube. And now we're going to be able to leverage this exponential, right? So at this point, it's linear algebra, but this is like a very nice idea of Litvak and Tikhomarov, which is to pass to the slice and exploit the anti-concentration on the slice. And this is the reduction here. And now I'll say something about this thing. But are there any questions about the linear algebra before I proceed? Okay. So unfortunately, this is the last part of the talk that's meant to be understandable. And now I'm going to wave my hands because the rest of the stuff is a little bit hard. But yeah, so let me just sort of show you what we want to show. So for instance, what I want to show is something of the form this thing, right? So let me just focus on the first row. It's similar for all of the other rows. So I want to show something. I want to bound something like the probability that the distance between the first row and the remaining, and the span of the remaining rows is small. And I have this information that, let's say, the infimum over almost constant vectors is not too small. And I can also assume that the first row is drawn from like the typical slice, right, of what it should be. So I want to control something like this thing. And okay, so I'll say like a couple of things, but I won't really do much here. But let me just sort of at least say what's going on here. So the point is, okay, I'm going to prove some structure theorem, and it's going to be defined in terms of the threshold function. But this is still a good idea to understand. So what is the threshold function here, right? Okay. So let's imagine, for instance, that you have this random walk, right? And what's the best case situation, right? Let's say it's like Gauss, like instead of these C1 to C and being like Bernoulli things or drawn from the slice, let's say they were like Gaussian or something, right? So let's say if like they were like independent Gaussians, then the whole thing would also be an independent Gaussian, would also be a Gaussian with like mean 0 and variance 1 because it's a uniform. Right? Okay. So this thing in particular has a density, and having a density is kind of the best thing you can hope for. Having like a density bounded by a constant is the best thing you can hope for anti-concentration. So if you have like a random variable with density bounded by a constant, then the probability of lying in any interval of length t is at most a constant times t. Right? So this is sort of somehow the best thing that you can hope for. This definition of threshold function, which was isolated by Tikhomarov, is asking what's the smallest length of the interval at which you can guarantee that from this point onwards, my random walk is somehow indistinguishable from a random variable with density, if that makes sense, right? So you're asking so you fix some L, and then you ask what's the supremum of the radius at which this thing is violated, right? With like density L, right? So let's say the supremum is T0. So at T0, this thing is true. But then for like values bigger than T0, I know that this guy is less than or equal to LT. So my random walk is somehow indistinguishable from a random variable with density at most L, right? So this is sort of the best thing that you can hope for. And ideally, what you would want to show is that the threshold is as small as it can be, right? So somehow that's going to be the idea. Okay. So what we do is prove a structure theorem, which is very similar, very similar spirit to the structure theorem we had before. So earlier we had this thing where we said, okay, the structure theorem is saying that any potential null vector must have many non-zero entries, right? Okay. So here we show something much more refined, which is that any potential null vector, right? So I look at the last n minus 1 rows, and I look at a unit vector perpendicular to the last n minus 1 rows. And you show that, okay, with extremely high probability, right? So probability in 4 minus n is certainly we can throw away, right? This is like smaller than our error terms. So with extremely high probability, any potential null vector is either close to a constant vector, is either like in my constant class, right? Or it has threshold function extremely small, right? And the point is that this guy is smaller than 1 minus p to the n by an exponential amount. So now we have this dichotomy that either my null vector is close to a constant. And I mean, again, this is something which is unavoidable because it could happen that my second row ended up being 0 or something, right? So not something I can do much about. So either my null vector is close to a constant, or it has like extremely good anti-concentration. Right? So this is the kind of structure theorem that you prove. And then given the structure theorem, you can imagine how you deduce this, right? So yeah, I don't think I even show this thing. But now the reduction is exactly the same as the following, which is you want to bound this thing, you expose the last n minus 1 rows. Now you have the structure theorem, and you can rule out the fact that x is a constant vector because somehow you know that the infimum of a constant vector is not too small. So I must be in this good case. And now the anti-concentration guarantees that the probability that the distance between R1 and H1 is like very small is 1 minus p minus epsilon to the 1. Right? So it's exactly the same reduction as before. So I'll just skip this thing. So yeah, in the last like maybe 5 minutes, I can't believe I've taken an hour and a half. Let me just say something about like how the structure theorem is proved, right? Okay. Yeah, so let me just say that the way that the structure theorem is proved is also by union bound argument, right? So previously we also proved a structure theorem by union bound argument, except now you have to like do some very precise accounting, right? And like one thing that you might do is you might look at this threshold function. You might just think of it as a function on the sphere for a fixed value of L, and then do some dyadic decomposition on the level of the threshold, and then just sort of do a union bound in each dyad, right? So that's somehow the idea. Okay, so this actually ends up working. The point is, in order to make it work, you need some very precise estimates for the union bound to go through, and in particular, you need some very precise estimates on the size of epsilon nets for like sets of this form, right? Now, if you've heard of like these so-called inverse Littlewood-Alpha theorems, this is actually what they were designed to do. So there is this distinguished line of work on inverse Littlewood-Alpha theory going back to Tao and Wu, then by Rudelson and Vershinen and Wu. I had some work with Asaf Ferber, Kalu, and Wojtek Somatich around this line, and then Tuan also has some work on this thing for like the slice. Anyway, the point is that you can do things like this thing, but they will place some restriction on T, which is not good enough. right? So these things will only work for t, which is, let's say, at most exponentially small, for like some small exponential, and certainly it won't go all the way through. So really, the idea of T. Komarov in his paper and which we build upon is to sort of move beyond sort of the traditional inverse Lilbert type theorems and prove like metric entropy estimates for sets of this form, going all the way to this value, right? And I will say like maybe one line about how to do this thing, right? So okay, so let me just say that we prove like some result of this form, and it's not like super important, I guess, for now, like since I'm not like giving any details what we proved, but just suffice it to say that the point of T. Komarov's result, right, was to prove exactly something of this form in the binomial setting, and somehow like the main technical, like one of the main technical things in our paper is to prove the corresponding thing on the slice, right? So for the slice anti-concentration. Let me just say something about what the point is, and maybe if you ever heard if you heard like T. Komarov giving this talk, or if you tried looking at this paper, maybe you read something about like inversion of randomness. So let me just say something about what's going on here. Okay, so maybe I discretize everything, and everything is nice, and the point is, okay, yeah, so I discretize everything, or maybe you can even forget about this problem and just think about the following integer problem. So let's say I have points on the integer lattice, right? So I have vectors on the integer lattice, and let's say I have like some condition on their coordinates. So their coordinates either lie between n and 2n, like half of them lie between n and 2n, and half of them lie between -2n and -n. The only reason is I want some separation because I know my vectors are like not close to constant, right? So it's some discretized version of this thing. And now you're asking, and now what you want to show is that you want to count how many of these vectors on your integer lattice have poor anti-concentration, right? So typically, the way that things work in like the Lilbert-Offered and inverse Lilbert-Offered framework was to say, okay, if my vector has poor anti-concentration, then I want to characterize the vector somehow, right? So in this like classical Tau framework, what they said is, oh, it must be the case that my vector is mostly contained in a generalized arithmetic progression of small rank, and then you can sort of like do some counting there. Then there is this paper of Rudolph and Vershinin where they like identify this thing called the essential least common denominator of a vector, and they say that okay, if my vector has poor anti-concentration, then the essential least common denominator must be small, and then you can also do some counting. The idea of T. Komarov is to sort of move beyond this thing and just work with the concentration function directly. So what he does is sort of think about things in the following way. So what everybody else was doing is they were fixing the vector, right? You fix the vector and it has some conditions, structural condition, and then you think about the randomness of like C1 to Cn, right? In T. Komarov's framework, what you do is you think about this function as a function on the lattice, right? So now I have like a point on the lattice, and now the lattice has the concentration function, and now you sort of like try to think about this thing as some sort of large deviations problem, right? So you choose like a random point on the lattice. What's the probability that it has bad anti-concentration? And now you want to prove some large deviations estimate, right? So you really think about the anti-concentration function as a function on lattice vectors. And now the randomness is coming in the choice of the lattice vectors. And really you do something like you sort of sample vectors on your lattice coordinate by coordinate in some sense, and then you sort of prove things, right? So he calls this inversion of randomness, which is instead of like fixing the vector and then thinking about sampling C's, you really sort of think about the anti-concentration function as a function of the lattice, sampling random lattice points, and then proving some sort of large deviation estimate, right? So anyway, this is something, and yeah, you can read like our paper or his paper for like an account of how to prove something like this, but this would like require like an additional like hour and a half or 2 hours to prove, right? Okay, and the last thing to say is that okay, one thing the thing I showed here is like the Bernoulli case. I said that like our result works for like general discrete random variables. And for general discrete random variables, instead of like looking at the slice, what you really want to do is you want to look at the correct multi-slice, right? So I have my random variable, which takes on, let's say, A1 with value P1, A2 with value P2, A3 with value P3. Then the typical slice is going to be P1 entries are A1, P2 entries are A2, P3 entries are A3. So you want to zoom in on a slice like this and do all of this analysis. This is like something which leads to at least the notation being much worse. The other complication is I only showed you how to do things when the dominant event for singularity is a row or column being 0. But in the general case, you end up in situations where like the dominant thing might be 2 rows or 2 columns being the same. So then the class of elementary vectors becomes more complicated, and then you have to do like quite a bit more work to analyze the class, right? But again, like the main ideas are in the Bernoulli case. So if this talk was of interest to you and you want to like learn more about this thing, so we wrote like a couple of papers on this thing. And the first thing, which is just sort of available as an archive preprint, has a self-contained proof for the Bernoulli case. And if you look at this, then like this fills in all of the details that I skipped through, including like a proof of the structure theorem and all of this like inversion of randomness stuff. And then you don't really need to read the general case, right? I think the Bernoulli case has like all of the important ideas already. So yeah, yeah, somehow I'm still 2 minutes over time, and let me stop here and thanks for your attention, and happy to take any questions.
Thanks a lot, Vishesh. Don't worry about the time; it's flexible. But it was a great talk. Thanks a lot. So maybe, yeah, let's unmute and clap or send the yeah claps like that. I'll clap myself.
Thank you.
Yeah. So I had a question about maybe along the lines of what you were telling about the kind of the number of terms in this expansion of this function. Is there any hope to kind of say that the first contributions to this function are, the first is two rows being identical, the first order of magnitude, or the row being 0, then two rows being identical or opposite, and then the third contribution is linear combinations on 3 rows and this kind of thing.
So there is in fact even like a conjecture by Conglocious Theorem stated in that form that like, so okay, I guess you have to like work out the thing distribution by distribution, right? Because for some distributions it might be coming from like I don't know, like 3 rows summing to 0, and for some other thing it might come from like things being the same. So you kind of have to work it out. But yeah, like you can like have like a general conjecture of this form that the first like constantly many terms, right, are coming from like things of this form, right? Absolutely, right. Yeah, so that seems like it should be true, right? There's no reason to suspect that it's not true. Okay, so here I showed like some case where we can get like 1 term, some case where we can get 2 terms, and then you might ask, okay, can you get 3 terms, 4 terms, 5 terms, and so on, right?
So this depends basically on this difference between the Bernoulli case and the uniform case, how good a concentration you get, or
so really like the way that we're about to go. So okay, let me sort of go here and say that, okay, so I said like what happens in the general case is we sort of zoom into the multi-slice, right? And if you zoom into the multi-slice, then you can think about what's happening to the anti-concentration, right? Like what kind of bound you can prove. You can prove something which is exponentially off from the entropy, right? So this is controlled by the entropy of the random variable. So I think what you can do is if you sort of work hard enough, then there is some hope of like proving enough terms, right? Like, okay, then you have to like do all of this analysis of elementary vectors, which is non-trivial, but maybe like with enough work, you can prove an expansion up to the point where you have this bottleneck coming from the entropy of the random variable. And beyond this thing, your anti-concentration is too weak. So that is disconnected, right? So now you might say, okay, well, now if you want to somehow go beyond that, maybe instead of working with 1 row, you have to work with like more rows at a time or something. But then things like get a lot more complicated, right? So I think like perhaps like the question before, like I guess like asking for more terms of the expansion would be to see if we can prove the correct result for the uniform distribution, right? So there is like a proposed result by Anwar Irmatov. Like he has like a claim for Bernoulli 1/2. So it's really specific to Bernoulli 1/2. But as far as I know, this is like still under review, and there was like some gap found at some point. Maybe that has been fixed, but it's like completely different set of techniques. So that is like still like it's the status of that is not settled. But even if that were the case, that kind of proof does not say anything about uniform distributions generally. So I think what would be nice to understand is what to do about uniform distributions. And here, I don't know. Yeah, okay, I think the result was somewhere here. And really, like here, we can sort of analyze the elementary vectors correctly, so that's fine. So they really think the constant vectors correctly. So really, the only thing to analyze is the non-constant vectors. And the problem that we end up with is that there is no gap between the thing that you have and the entropy. Right? So that's sort of the problem, and you need like some like another idea to sort of go beyond.
Yeah, and here at this moment, this little n of 1, it's still super polynomial, right? It's a super polynomial.
So if you write this thing, it's going to be like, let's say the support is of size k, so it's going to be 1 over k to the n times some super polynomial. Yeah. Absolutely.
Okay. Great. Now that was very interesting. Dense, but I managed to follow most of the things, I think, and I hope other people also enjoyed it. Yeah, thanks a lot, Vishesh.
Well, thank you so much, Andre, for the invitation again, and everybody for sticking around. I mean, I know it's a long talk, and I know it's late in Russia, so thanks.
Yeah. Yeah, thanks, and hope to see you sometime soon in person.
Absolutely.
Okay.
Thank you.
Bye, everybody. Bye, Vishesh.
Bye.